talk about partial fraction decomposition, right? Or we'll just call it PFD for short, okay? This is an integration technique that's actually borrowed from pre-calculus. I seriously doubt that you learned this in pre-calculus because nobody in pre-calculus ever wants to teach this. And honestly, if you're learning it in college, there isn't time. But we can talk about it here. So this is actually a technique that has very little to do with integration. The integration part is the easy part. In fact, you do all of this work so that you can get down to something. So basically the point is that we can't easily integrate things that look like this. So if I put x minus 2 here on top, and then let's just put a couple different factors in here, 2x minus 1 squared and x minus 1, okay? So I can't do that easily. There's just absolutely no way that I can take the integral of that very easily. I see some different function compositions going on here, but this isn't a clear U substitution. I could try an integration by parts here, but no matter how you slice it, it's not going to work out real well. And then there's just no trigonometry to be had here at all. So really, there's nothing here for us. So I have to do a partial fraction. Now I know that I'm going to see a partial fraction because of a couple of things. One, I notice that p of x, which is what we call the polynomial on the top, is less than q of x, which is what we call the polynomial on the bottom. So as long as the degree of the bottom is bigger than the degree of the top is 1, the degree of the bottom is 3, 2 plus 1 is 3, then we have that you can do partial fraction decomposition on this. And the only thing that we say is this. We say, gee, it sure would be nice if we could break this thing apart and write it a different way. So I'm going to write this guy right here, I'm just going to say equals, and I'm going to write him a completely different way. Okay? I'm going to say it sure would be nice if we could take this 2x minus 1, and it would generate something like minus 1. It would generate something like this, for example, because these things right here, that's still a minus, would be very easy to work with. And then that x minus 1, well, what if that were to pop out something like this? Okay, so this is what we're working with right now. We are taking, this is a true statement. This is a true statement. The thing up here in blue, this thing right up here in blue, is equal to all this stuff down here. So then, and I'll do it in red, if you were to take the integral of this dx, that would be the same thing as the integral of all of this dx. And then you just take the integral of each part of that individually, and that's just a very basic natural log of the absolute value of yada yada, right? So it becomes actually a really easy problem. So the question is, where did this stuff come from? How did I actually do the partial fraction decomposition? And I've got great news for you. It's just this table right here. So all that text right there just says make sure that the degree of the top is less than the degree of the bottom and factor the bottom as much as you can. But the rest of this, it gives you 4 different kinds of factors that you could be working with. The top, these two over here, rather on the left, these two here are single factors, and these over here are what are called repeated factors. No matter how that works, it's going to just be looking at it very briefly. So for example, let me show you. Let's use one that only uses this kind of factor, just literally linear factors. So let's say that you wanted to break down, it does not matter what's on top as long as the degree is less than what's on the bottom. X minus 1, and let's say x plus 2. Okay. Here is how that breakdown would go. You do not care about what's on top. What's on the bottom, you check each one of them. This guy right here is just of the form mx plus b, so it's going to generate a term like this. Okay. This guy right here is also of the form mx plus b, so it's also going to generate something like this. So here's what this is going to look like. We're going to say this equals, and I'll use blue for the actual color. Okay, this is just going to equal just sum a. It says a right there. So sum a divided by, okay, and then x minus 1, okay, plus sum b divided by x plus 2. Okay. And from here you can do a bunch of math to figure out what A and B are. And it's an incredibly easy thing to do, and we'll go through that in just a second. But that's all that you're really doing. You're just using this partial fractions table in order to figure out what's what. All right. So while I still have you here, let me see if I can grab this and not do that. Instead, let me just grab this real quick and let's just trash that. Okay, let me do another breakdown real quick for you. So let's say that you had, again, it does not matter what's on top. I can write anything in the world on top here. Let's do it in blue. So let's write x squared plus 2x minus 4 on top. And as long as the degree of the bottom is 3 or greater, I'm good to go on this. So that'll be just fine on this. And then let's write, say for example, let's do a repeated factor just so I can show you how that works. So 2x minus 3, let's say, to the third. So the degree of the bottom is 3, the degree of the top is 2, so we should be good to go on this. What we're working with is we have something of this form here now. So the thing on the bottom is something of this form. It's a linear factor raised to some power. In this case, this k is 3. Cool. So we just use this here. And what this says is this is just going to pop out a bunch of different values. So it uses A1, A2, A3, A4, A whatever. I just use the alphabet. So all it says is this. There's going to be 3 different terms. Okay. So there's going to be some letter, start with the first one, over just the thing by itself, just the linear term by itself. Okay. So 2x minus 3. Okay. And since it's 3, there's going to be another one, 2x minus 3, except that one's going to be squared. And then we're not up to 3 yet, so we got to do another one, 2x minus 4, 3 rather, 2x minus 3. Cute. And this would be the setup for the linear, for the different factors here. So that's all that it's saying. So in this case, k was 3, so you only go up to 3 factors. You just keep iterating up, and that's why I knew where to stop. And from here, it's just a little bit of algebra to get this finished. Okay, so that's that kind of thing. All right, so let's look at one more of these. Let me delete that. Okay, and then let's look at one where it's kind of a mix. Okay, and I could do one where, in fact, all of them showed up if I wanted to. But let me just show you this for a second. And by all means, pause the video and see what you can do with this. But let's put just x plus 2 on top. I'm just making this up. Okay, and let's put the factors very clearly as, let's put 2x plus 1, and then let's multiply it by a different one. That's 3x squared minus 2x plus 1. And let's square the whole thing. And that's about as complicated as I can make one of these, okay? And so you need to look at these factor by factor. So look at this factor over here first, the orange factor over here first, okay? Don't worry about what's on top, just look on here. So this is of the form 2x plus 1, so it's going to be one of these guys right here. It's going to pop something up of the form a, because we haven't used it yet, over 2x plus 1, okay? So 2x plus 1, and that's going to be that first factor, okay? Plus, okay? And then the next one is this purple guy here is a quadratic raised to the second power. Well, that's something of this form. So it's going to generate 2 different terms. It's going to generate things up to k. So the first term is going to be, the next letter that we haven't used yet is b, divided by 3x squared minus 2x plus 1, okay? And then the next term is going to be, well, the next letter is c, not to be confused with the constant of integration. And then we need to do 3x squared minus 2x plus 1 all squared. Okay. If this thing were to the 12th power, then we would do another copy of this. We would do d over this polynomial to the third plus e over this polynomial to the fourth, so on and so forth, all the way until 12. And that's it. You really only need these bottom 2 here because these top 2 are just special cases. Or rather, you really only need these 2 on the right because the 2 on the left are just special cases where k equals 1 for the right. That's all that you needed if you just want to put less in your notes. But this really is how you put together a partial fractions problem. So from here, you're just solving for A, B, and C, and it can be a bit of a bear. It's just a ton of algebra is all that it is. And I'll show you that in just a second. But the important part is that if you're going to integrate, that's an integral sign, dx of something of this form, well, that's the same thing as integrating something of this form, which means that you can actually just integrate this part, and then integrate this part. And those are all really quick little natural logarithm integrals that you just have. Whereas this guy over here on the left, this guy over here, is incredibly difficult, if not impossible, to just integrate by looking at. So that's what we're talking about, all right? So let's actually do an integral now. Let's do one that's pretty well put together. So we're going to do an integral, and let's do an integral, say, of x minus 2. Let's say x minus 2, okay, divided by, and then let's do 2x minus 1 squared. 2x minus 1 squared over times x minus 1 dx. Okay. So you need to go do the partial fraction decomposition, and we'll come back to this in a second. So there's two different factors that'll come out of this. There's this guy will generate a couple of factors, and then we'll do orange for this guy will generate a single factor. So let's do that factor. So I'm just going to come down here and do the partial fraction decomposition. So we'll come back to the actual calculus. So I'm just going to rewrite the integrand here, the thing that we're taking the integral of. So x squared over 2x minus 1 squared times x minus 1, okay? And then I'm going to say this is equal to, and now I'm going to pop out those factors real quick. So in purple, 2x minus 1 is going to pop out two factors. Because we have squared this guy here, it's going to pop out, our first letter is always a, so a over 2x minus 1. And we haven't got up to 2x minus 1 squared yet, so now we're going to do b over 2x minus 1 squared. If that was 2x minus 1 cubed on the bottom, then I would also add c over 2x minus 1 cubed. And if it went all the way up to the fifth, then there would be a third, fourth, and fifth power on the bottom, and I would go a plus b plus c plus d plus e, and that would be it. Okay. And then the second guy here, I'll put a plus just from the stuff that I put together. The second guy here is literally just going to produce c over x minus 1. Because that's all that it is. It just produces the first one. You only go up to 1. So that's it. So from here, we're just going to do a little bit of rearranging. So I'm going to do what's called clearing denominators. So in order to clear denominators, what I'm going to do is I'm going to multiply everything here by the entire denominator. So I'll do that. I'll do that here, and then I'll do that here as well. Okay. And I'm just going to multiply everything on both sides by this entire denominator here. Well, if I multiply the left side by this denominator, it'll cancel this. Okay. So really what I'm doing is just multiplying every term over here. I'm multiplying every term over here, okay, multiplied by 2x minus 1 squared times x minus 1. Okay, so this term here is going to get distributed, this entire term, and this entire box is going to get distributed to this guy, and to this guy, okay? So this is going to look actually quite terrible. So the thing on the left that's left is x minus 2. So let me show you that. So the only thing on the left that will be left is just x minus 2, and it'll always work out this way, okay? And then we want to look at this. So, when you multiply a over 2x minus 1 times this whole thing, it'll cancel one of these guys here, and you'll be left with a times 2x minus 1 times x minus 1. If you don't believe me, just write it down. But you get, let's see if I can get all this on the same sheet. You get a times 2x minus 1, because one of the 2x minus 1s, this one here, canceled with one of these 2x minus 1s, is what I'm saying. So you'll be left with a times 2x minus 1 times x minus 1, okay, plus this entire 2x minus 1 squared will cancel with this entire denominator, so you're going to get plus b times x minus 1. You're going to get plus b times x minus 1, b times x minus 1, and then In this next one, this x minus 1, remember this factor is distributed times all of them. This x minus 1 will cancel with this, and you'll be left with just this guy. So it'll be plus c times 2x minus 1 squared. And if you want to see this, this is actually example 3.32 in your OpenStax book in section 3.4. It's already done for you here. So you've got everything put together. This is how everything's put together here for you. And so you're just going to put your coefficients together. And so all that this is going to involve is very simply just multiplying all this junk out and grabbing everything together. So this is actually when the god-awful algebra hits. We actually have to multiply all this stuff out. So let's just do some algebra now real quick. So it's still x minus 2 on this side. So x minus 2 on this side. I'm going to distribute this a through last. So I'm going to multiply. Let's FOIL these last two guys out here. So let's see here. This will be a times... let's see, 2x times x is 2x squared. 2x minus 1 is minus 2x. Minus another x is minus 3x plus 1. Okay, that's that. That's plus bx minus b plus... And then this will be c times, and then I need to actually do 2x minus 1 squared. So 2x times 2x is 4x squared, 2x times minus 1 is minus 2x, minus another 2x is minus 4x, minus 1 is plus 1, okay? So now I need to distribute through the a and the c. So my next thing will give me x minus 2 equals, let's see here, this is 2x squared a minus 3x a. You usually want to put your a's, actually, let me do that. You usually want to put your a's before your x's. So let's do 2ax squared minus 3ax plus a plus bx minus b plus 4cx squared minus 4cx plus c. Okay, now the big deal is just get all of your terms together. Get all your x squareds together, all your x's together, and all your constant terms together as well. And then we'll group it together, and you'll see what we're doing here. We're just going to match coefficients over here. So this is actually, and I'm going to, on purpose, scoot this x minus 2 over a little bit because I'm going to do something clever in a second. So all the x squared terms. We have a 2ax squared, okay? And sometimes I like to go through and just mark them out when I've copied them down. So a 2ax squared and a 4cx squared plus 4cx squared, okay? There don't appear to be any more x squared terms. Now let's go do all of the x terms. So minus 3ax, okay? I see a plus bx. And I see a minus 4cx, okay? And then that's all of the x terms. So then there's plus a minus b plus c. So plus a minus b plus c. Okay. So if you notice something, this is a plus, or I guess I could do, let me see here. Let me erase that real quick. That was a minus. I can write it as plus a negative, but let me rewrite that as a plus a negative. So let me write that plus a negative. Then you can notice that you can just group these things together like this, right? Group all your x squared terms together, group all your x terms together, and then group all of your constants together. Now, notice when you do this, just make sure that you don't have a negative sign out here that you need to end up distributing through, and it changes everything. So you saw how I did that plus a negative so that I can make that happen. Just be careful with that. So we're actually just going to now factor out the common terms. So let me show you the common terms. I'm going to highlight them all. The common terms in this guy is x squared. The common terms in this guy is x. And then the common term in this guy is, 1, but that's just going to be left alone. So the last step in doing this absolutely hellacious algebra is just we're going to do x minus 2 Okay, we're going to factor out the x squared, and we're going to put it after the thing that we factored out. And you'll see what we're doing here in just a second. So we're just going to factor that out real quick. So this is going to be 2 times a plus 4c times x squared plus, okay, and then it's going to be not minus 3a plus b minus 4c, that's 4c, times x plus, and then a minus b plus c. Okay. So now, believe it or not, we have everything that we need in order to actually solve for the precise values of a, b, and c that make this possible. After that point, you have the partial fraction decomposition that we need for the problem, and then literally the entire thing that we're doing, the whole thing that we're doing is just, and very, very simply, just pattern matching and then shoving this into a very basic integral. The integration, the actual calculus of this is insanely easy. So let me show you this. Notice over here on the left side that there is in fact a 0x squared. That's why I scooted it over. Okay, and there is also, you would agree, there's also a 1. Let me write this plus, very tiny, plus. There's also a 1 in front of this, okay? So look here. The thing in front of the x squared is 0. The thing in front of the x squared is 0. Let me try and get this just right. The thing in front of the x squared is 0, and over here, the thing in front of the x squared is 2a plus 4c. We're just pattern matching, okay? Notice over here, the thing in front of the x is a positive 1. Notice over here, the thing in front of the x is minus 3a plus b minus 4c. Okay. Notice that in red. Notice that this is minus 2. Notice here that it's a minus b plus c. We have a system of 3 equations, and that's all that this turns into. Very basic algebra. So we now have a system of 3 equations. Here's the system of 3 equations. In orange, we have the 0 from the left-hand side equals 2a plus 4c for the right-hand side. I'm just going to flip that because I can. So I say 2a plus 4c equals 0. Okay. Then in purple, we have negative 3a plus b minus 4c equals 1. And then on the right side here, the last little bit that we have is the a minus b plus c, and that has to equal negative 2. So a minus b, so a minus b plus c equals negative 2. Okay, that's it. That's the entire thing. So you can now solve this in any way you want to. For those of you that are in linear algebra, by all means, get this thing into a matrix, use reduced row echelon form. Remember that missing things, like this guy up here is missing a b, well, that's plus 0b, all right? Get that thing into reduced row echelon form and give me the values of a, b, and c. That is a really quick way to do this, of course. But if you don't know what reduced row echelon form is, if you've never seen a matrix before in your life, other than the incredible 1990, I believe, 9 movies starring Keanu Reeves as Neo, as the matrix, in which case you need to just solve this using substitution. So in general, you just pick something that looks easy and you try to solve for something in terms of something else. So we take, and the only real rule here is that we do everything in our power not to plug values back into an equation that we've already solved for that value in. Otherwise, we just get circular reasoning. But for example, if I just, I could solve for c in this first one if I wanted to. So you would agree that if I subtracted over 2a, I would get 4c equals negative 2a, and then I could just divide by 4, right? I could just divide by 4, and I would get that c must equal negative 1/2 a. And if you don't believe me, just do that. Subtract the 2a over, you get 4c equals negative 2a, and then you'd have negative 2a divided by the 4 that you divide by. Negative 2 divided by 4 is negative 1/2. So now, in this next problem, if I wanted, I could replace the c here, this c here, with negative 1/2 a, and that would simplify that down a little bit. But I see that the third one is an even simpler thing, so I'm going to plug it into that instead. So I'm going to use this piece of information here, and I'm going to plug in c right here. Okay, so I'm going to write then that this gives me that a minus b plus negative 1/2 a equals negative 2. And so just solving this really quick, well, this is a plus negative 1/2 a, so then that gives me that 1/2 a minus b equals negative 2. And I can probably solve for b in terms of a from this one, or a in terms of b for this one, and that would probably be a little bit easier. It's however you want to do it. So let's solve for a in this one. Let's just decide to do that. So I'm going to add b over, so that's going to give me 1/2 a. That's a half. That's so bad. 1/2. There we go. 1/2 a equals negative 2 plus b. Okay, or b minus 2, which is how I'm going to write it in a second. And then I'm going to multiply both sides by 2. So that's going to give me that a equals 2b minus 4. So now I have another way to write that. So I have a in terms of b here. So that's cool. So now maybe I can come here and, I don't know, I can write a in this equation here, and also a again here, because I've already solved for a here as well. So I know I've got both c and b in terms of this. I can do a whole lot of stuff with this. So let's replace a couple of values in this bad boy here. So it would be helpful if I could get this down to just one thing. So I actually have c in terms of a, so if I had b in terms of a, that would be really useful. So let me get b in terms of a. So add 4, divide by 2, and that would give me that b is a plus 4 divided by 2. That would be a little bit easier. Yeah, let's just do that instead. So yeah, let's go with that instead. So just because we want everything in terms of a, I already have something in terms of a here. That is, c is written in terms of a up here, and now I have b written in terms of a here. I'm going to use both of these pieces of information, and we will have a single equation. So watch this. This is minus 3a plus, well, b is just a plus 4 over 2, so plus b is plus a plus 4 over 2, so that's 1/2 a plus 2, if you'd rather write it that way. That's what b was. And then minus 4 times, well, c was negative 1/2 a. Okay. So then this can come on down here, and we can simplify this down. Negative 3a, oh, this has to equal 1. So then we just solve this for a. I mean, this is all in terms of a. So negative 3a, let's see here. When you multiply this through here, minus 4 times minus 1/2, this will give you a plus 2a. So let's see here. We have minus 3 plus 1/2 plus 2. Well, minus 3 plus 2 is minus 1. So minus 1 plus 1/2 is minus 1/2. So we have minus 1/2 a. This gives us that. Minus 1/2 a, and then all of the constants added together. Let's see here. This will be 2. That's it, plus 2. That's the only constant left over. So plus 2. Yeah, plus 2. Plus 2, that has to equal 1. That's the equal 1 that we're getting from right there. So minus 1/2 a plus 2 equals 1. So subtract 2 over. You get that negative 1/2 a equals negative 1. And then multiply both sides by negative 2. So you get that a must be positive 2. Awesome. So you get that a has to be positive 2 in this. And that is fantastic. So now we actually have a value. We have a value. I'll put some pointy ends on it so it's easy to find. So we have a value there. A equals 2. Now we have a equals 2, and we have a bunch of other formulas, so we can go back over here and take anything. Well, if we know that a equals 2, let's just plug in 2 here real quick. So I'll do this in blue. okay, I'm just going to plug in a equals 2 into this guy. So a equals 2 into this guy, let's come down here. A equals 2 plus 4c equals 0. So that's 4c plus 4 equals 0, which means that subtract the 4 over, divide by 4, c must be negative 1. So now we have c equals negative 1. Awesome. So c equals negative 1, okay. A equals 2. Well, if that's the case, then we can just plug both of those values into, I don't know, this guy and get what this equals. Let me do this guy in purple so it's in a different color. But I'm just going to plug that in. I have that a equals 2, so it's a minus b plus c has to equal negative 2. So I'm going to do a, which was 2, minus b, which we don't know yet, plus c, which is negative 1, has to equal negative 2. Well, now we can solve this for b. I'm going to add a 1 over and subtract a 2 over, or you can just notice that 2 minus 1 is 1. This is 1 minus b equals negative 2. And then it would give us that, let's see here, negative b equals negative 3, or b must equal 3. Now we have all three of our values. Let's collect it all in the same place. So we have a equals 2. I'll write it over here. We have a is 2. We have a equals 2. B equals 3. And c equals negative 1. Okay? So you have that piece of information. Now, where were the A, B's, and C's coming from? Well, the A's, B's, and C's, that's what goes here, here, and here. So I'm just going to put the equals there and show you how this works. So 2, 3, negative 1 were the numbers. 2, 3, negative 1. So I'm just going to say this equals 2, this equals 3, this equals negative 1. Okay? So that this original integral, now this is the actual, this isn't even the calculus part yet, actually. This original integral breaks down into 2 over 2x minus 1, okay, plus, okay, and I could do plus and put the dx way out here, right, but it's actually going to break down into three different integrals, so I'll save us a step and just break it down into the three different integrals now. So dx plus 3 was apparently the top over here, over 2x minus 1 squared dx, okay, plus the integral of, well, apparently, negative 1, well, negative 1, so we'll write a minus, I guess, integral of 1 over x minus 1 dx, or I could have written dx over x minus 1 if I wanted to, whatever. So the way that ends up working is you just now do those integrals really quickly. So these integrals end up evaluating to, I'll do the evaluations in purple. This evaluated right here, this is just 2. You pull the 2 out, and so it'll be 2 times the natural log of the absolute value of 2x minus 1. That's what that evaluates to, okay? This guy right here evaluates to the natural log of the absolute value of x minus 1. X minus 1, that says, okay? And then this guy right here evaluates to negative 3 over 2 times 2x minus 1. How do you do that part of the integral? Well, this is just a baby u substitution, but I'll leave that to you to do. But it is just a simple little u substitution because you've got a 2x minus 1 plugged in here, right? And its derivative up to a constant is just a constant, and there's the constant sitting in there. So let your u be 2x minus 1, and then just do the u substitution and plug things back in, and it'll end up working out for you just fine. So 2x minus 1, like that. So if you wanted the actual answer, it would be, let's see here, this term minus this term because it's negative, and then minus this term, and then you would tack a plus c on the end. And that would end up being the entire answer. So is this a long and laborious process to do this entire thing? Yes, it is. It is an incredible amount of algebra to go through and do all of this. Absolutely. It took me 35 minutes to explain and work through this problem. But this algebra right here that we're doing is stuff that you were learning in 8th and 9th grade. It's a basic system of equations that you're plugging in. And if you want to hit this thing with linear algebra, guys, it'll go even faster. So that is an example and a little introduction to this sort of thing. This is already a 35-minute video, so I'm not going to make it an hour by adding in another one of these. But this should get us a little head start when we go into looking at this next time. So best of luck to you. By all means, try the problem again or slightly change some of the numbers here. You're more than welcome to do that. Just change some of the numbers. Literally just change this 2 to a 3, change this 3 to a 5, this 2 to a 6, and this 1 to a -2 or something. And you would get a completely different problem, and you're more than welcome to try it. Or just try a few from your book. And I would love to talk to you about this next time. So we'll see you around then. Hope you learned something.